I'll present to you my work on money laundering detection using graph neural networks enhanced with autoencoder components. I'll start with a definition of what the money laundering process is, go into some details about the graph neural networks architecture, some details about autoencoders, continue with a literature review in the domain. I'll explain our approach, including the original contribution, the dataset, and the architectures, and provide some details about the comparison to related work and some explainability results you obtained using SHAP, as well as some conclusions and potential future work that can be done. So, money laundering is a complex process of obfuscation in which criminal parties seek to make illicit funds hard or impossible to distinguish from those acquired by legal normal means. Financial institutions typically implement electronic anti-money laundering systems, which in actuality function as an alert systems that escalates messages that are further reviewed by data analysts. This escalation mechanism typically relies on making sure that all fraudulent transactions, or as many as possible, are detected, which most often results in having a very high false positive rate, quite often even close to around 90%. And traditional approaches are typically rule-based systems. Now, graph neural networks are an architecture that is capable of handling data in a graph structure. The most common approach for developing graph neural networks is the message passing neural network framework. It works using, as the name implies, a system of messages in which a node aggregates messages about the features of its neighbors and updates its internal states based on these messages, and quite often features of the connecting edges are also included. Then as I said, we update the internal states of the nodes based on the aggregated features. It can be formalized as such. A message that corresponds to a node is updated from the aggregation of all the features from its neighbors. Here is a more graphical representation in which we create the messages. They are aggregated to a central node, and the node proceeds in updating its hidden state. Now, autoencoders are a class of neural networks that corresponds to the self-supervised machine learning paradigm. And the models, the autoencoders, function by learning how to reconstruct input data based on lower dimensional latent representations. Here's a general overview of such an architecture, in which we lower the dimensionality of the input data until we reach the middle bottleneck layer. And the first part consists of the encoder. Then the second part, the decoder, learns to reconstruct the data from the latent representations. Graph neural networks have been used successfully for anti-money laundering tasks. but the research on autoencoder enhanced or autoencoder graph neural networks for money laundering detection is pretty sparse. For example, when it comes to normal graph neural networks, we have approaches using skip connections for money laundering detection in Bitcoin transactions. We have approaches done on what we can call real life data. For example, Johansson and Julum used an approach implementing graph neural networks for detecting money laundering in a network of transactions from the largest Norwegian bank. Egressi and all have multiple approaches in which they combine key adaptations to standard graph neural networks in order to render them a better fit for graphs of transactions. These adaptations we also implemented as part of one of our architectures. And the Shu et al. Combine a rule-based system with anomaly detection and graph neural network to detect financial fraud. Our original contribution comes from the fact that, to the best of our ability, we have not identified any other approach using an autoencoder enhanced graph neural network for the purpose of detecting money laundering. And as part of this research, we seek to answer 3 research questions. The first is whether integrating autoencoder components into what we consider to be an edge classification problem improve the predictive performance of money laundering detection. Second is if the integration of autoencoder components in an architecture that's enhanced in order to handle more complex data remains beneficial or not. And the third question is whether what are the most significant features for detecting each type of transaction, namely a normal transaction and a fraudulent one, as provided by the SHAP explainability approach. Now I would like to briefly mention why we've chosen this approach. We theorize that by using an autoencoder, the nodes will be a little bit more inclined to preserve and encode features that are more important for defining the edges in their close proximity. And most importantly, as the detection of money laundering relies for the most part on the observation of fraudulent and most of the time well-defined patterns, we also seek to handle the cases in which the patterns are more novel, and we presume that fraudulent edges have some, albeit variable, specifics that ultimately make the representations deviate from expected patterns, and this will be reflected in the reconstruction error. Now, as for the data set and the training procedures of the model, they are pretty standard, in which we use graphs of financial transactions. They are synthetic transactions created using a multi-agent system from IBM. The models are trained on the transaction graphs. The autoencoder encodes node embeddings and attempts to reconstruct the edge features based upon the node embeddings. The reconstruction is done on a feature by feature basis, and at the end we aggregate the results. And in order not to bias the model too much, we weight the error given by the autoencoder by a factor of 0.1. And in order to evaluate the results, we use the F1 score of the minority class. Now, a bit more background. Graph representations are typical, in which we have nodes and edges. The transactions are represented as edges, but what's typical of transactions is that they have a source and an end. As such, the edges are directed, and pairs of accounts can have multiple edges between them, which is why we can refer to the graph as directed multigraph. Here's an example of such a graph of financial transactions. The red arrows depict fraudulent transactions. Red nodes are nodes involved in fraud. And blue nodes are nodes that do not commit fraud, and green arrows are clean transactions. As for the data set, the whole corpus of the data set is larger, but even the smaller subset of the data has a large amount of transactions. Here we use the higher illicit subset of the data, because even though it's less representative of real life scenarios, the proportion of laundering transactions and the fact that still we have a much smaller amount of laundering transactions than normal transactions are going to still serve as a limitation, which would be exacerbated if we had an even lower laundering rate. For the purpose of our experiments, we've trained two different architectures in which we use these training hyperparameters commonly between them, a lower learning rate in order not to bias the model too much on the training data. We used neighborhood sampling mostly due to computational constraints, as even the least demanding model takes a very long amount of time to train. We weight the binary cross entropy part of the loss for normal transactions with 1 in order not to bias the model too much towards them. And the weight for fraudulent transactions is much higher, as we seek to, most importantly, identify the fraudulent transactions as well as we can, and we can tolerate, and the high false positive rate is tolerated in real life scenarios. Now, the first architecture is based upon GIN. We use an encoder with 2 layers, 2 hidden layers, 2 GIN with edge feature convolutional layers for the message passing procedure with batch normalization, and the final encoder layer to project the data to the latent space. We have a single layer decoder, again, due to computational constraints, which attempts to reconstruct the edge attributes, and the classifier, which takes the latent node features, the original edge attributes, and the reconstruction error, and passes them to 2 dropout layers and an NLP. in order to make the final prediction. The second architecture is based upon PNA. Now, PNA is more advanced in the sense that it has a component named towers that learn to focus on different parts of the data. And also some scalers that can scale different messages coming from different nodes and give some more or less importance. And besides this, we also implement some adaptations that were discussed in the paper Regressi et al. That I mentioned. We implement reverse message passing in order to handle incoming and outgoing messages separately. Typically, only incoming messages are handled when updating the vertex. Ego IDs, it's a flag that allows a node to detect whether it is part of a cycle. And for numbering gives unique labels for each node. These three adaptations help for making a model able to detect cycles better than more traditional approaches. And another adaptation is that the encoder and the decoder are now symmetric, in the sense that the decoder has two hidden layers now as well. When it comes to our results and comparison to related work, we can see that our first approach, gene plus autoencoder, offers better performance than the baseline gene model, which is encouraging. But when we look at the second architecture called multi-PNA plus edge updates plus autoencoder, we can see that the results are quite significantly worse than the baseline multi-PNA plus edge updates. We theorize that in the first case, as we have a homogeneous graph, the autoencoder is able to reconstruct such structures much better than in the case of the heterogeneous graph. The heterogeneous graph is constructed due to the use of reverse message passing, which uses two separate layers, one for incoming messages and one for outgoing messages. And we theorize that by strictly for the purpose of reconstruction, handling the heterogeneous graphs as two homogeneous graphs, we would obtain better results, but we haven't gotten around to testing this scenario yet. Now for explainability, we use SHAP values that have roots in game theory. The SHAP values are computed using an XGBoost model that's hyperparameter tuned, and the graph features are converted to a suitable tabular format using the SnapML library, which has a graph feature preprocessor fit for such a task. We have observed that the most important features are the payment format and also features which refer to patterns, such as the number of neighboring nodes, the number of transactions of a node, the ratios between them. Here's such an example. We can see the payment format is clearly the most important, as well as the number of neighbors of a starting node, the ratio of the neighbors and transactions of a starting node, as well as the same ratio at the end node. The amount sent and the amount received are not that important when we look at a global overview, but When we look at individual transactions, we can see some noteworthy findings in that the payment format remains the most important factor, and in this case only the source ratio, the ratio of neighbors to the transactions of the source node make the transaction more likely to be fraudulent. But when we analyze the distribution of this feature, we have seen that when compared to a fraudulent transactions tend to send sums and receive sums that are above the median, but well below the mean, and definitely very, very rarely with very small values, which is interesting in the sense that rule-based systems, from what I found, seek to only automatically label transactions that have very large sums of money implicated, which this might signal that the data was made in order to debias models from such scenarios. Now, when we look at a fraudulent transaction, we see that the most important features, besides the payment format, most of them refer to statistical features of the timestamp, as all the features with column number 3 refer to the timestamp column. And the edge ID can be considered as a proxy for the timestamp column as well, as they start from 0 and get incremented in succession, which tells us that the fraudulent transactions were likely generated by the researchers later in the process than normal transactions, which is also echoed by the timestamp, as these two quite often, but not always, seem to be correlated. And while this introduces a significant amount of bias for this specific scenario, we think deeper insights into how the data was generated and insights that weren't mentioned by the researchers still serve a good purpose in determining the usefulness of the data. As for our conclusions, we can state that our approaches for enhancing classification performance for homogeneous graphs renders very promising results, but the performance decays significantly for heterogeneous graphs. Payment formats and the number of neighboring nodes at the starting nodes of a transactions have significant predictive capability in determining transactions, and this is not affected by the timestamp bias I've mentioned. When it comes to future work, we seek to implement more complex autoencoder components, as I've stated, implement autoencoder components on other GNN architectures, and develop a SHAP adaptation for explainability on edge labeling tasks that is directly applicable to GNNs. This was my presentation. Thank you. If you have questions, here are the references.